So, good morning. Welcome to lecture 7 on thermodynamics of materials. Today we are a bit late. Maybe we have actually lost 15 minutes, but we'll continue with the reversible. With the reversible and irreversible process. So, the point that I want to note now is this, with a question. We'll start with a question that why is the reversible process named reversible process? This actually struck me when I was studying. So question is, why is the reversible process named so? Why it is reversible? We know we are carrying out with an infinitesimally small driving force, making the system move through a continuum of equilibrium states. So, but why it is reversible? So, come on, answer. The process, a reversible process can be reversed. A reversible process can be reversed without producing permanent changes elsewhere. A reversible process can be reversed without producing permanent changes elsewhere. Elsewhere means here you have to understand it is surrounding without making a change in the surrounding. So that is surrounding. We are referring to surrounding. Or that is when a reversible process is reversed, in other words, is reversed not only system returns to original state, surrounding also. So both system and surrounding returned to their original state, means initial states. Same thing. System is returned, surrounding as well returned. Still, that is, in other words, there is a perfect, maybe more easy to recognize. There is a perfect backtrack of the forward path. When a reversible process is reversed. So I have given 3 ways to identify a reversible process. I will explain this. Consider our simple example. For example, take this example, isothermal, reversible isothermal, as I told you, with ideal gas, PV diagram, just consider. I will show you. So, this is the forward path, 1 to A. What is this? Expansion. the reversible expansion of ideal gas, n moles of ideal gas. You have number of times seen this curve. So this is a forward path. So if I want to take the compression, reversible come back to 1, it can be exactly, it will retrace the path, not drift from it. This is the beauty or characteristics of the reversible process. So it is forward is expansion, backward is compression, or in other words, system moving from state 1 to state 2. And that's state 2 to state 1, state 1 to state 2 through 1A2, and returning from 2 to 1 through 2A1. Exact reversal, hence the name reversible. These are also producing same effects. That is actually both system, when this happens means both system and surroundings are returned to their original state. The same means, same. Or this, there is no permanent change in surroundings means surroundings return. When system, reversible process is reverse means system is taken back, then surrounding, there is no change in surrounding, it is also returned. They are returned to their respective initial states. And very easily from the diagram. Easily, sir. This will return. Okay, very good. Then why this is let us explain this more. Can we remove this? Explain this further. So let us, with the help of the experiment, please follow me, then you will easily understand. I am taking that gas. Oh, one thing I missed. Can you have you noted this? And initially, one thing I was pending last class, that analytically that reversible work is greater than irreversible work. I could not show you, okay, but this can be shown analytically. But this I will, okay, don't worry. N moles, don't worry, I'll take up this. N moles ideal gas as system. Don't worry, consider this. So this is, follow this. You know very well, this is the state 1. As you know, reversible, I am not writing all this. It is implied when I write T1, V1, T. And state 2 is, how do you reach there? State 2, T2, V2, T, quickly. So how the process was executed? Follow. Reversible forward. So forward means this direction. Expansion. Taking from state 1 to state 2 is an expansion of the gas. And how the process was executed, please follow me. P1, then recall P1 minus dP, then P1 minus 2 dP, and goes on like this until it is P2 plus dP, P2 plus P2, like this. So this is the forward expansion. This is the expansion. So forward path. Forward path you can write expansion. Right? Expansion. What is the reverse? Bring the system from state 2 to state 1. Compression. How will you carry out? When you see this, if this is this, I will say this direction. You start P2, start with this. It is here. Reverse. Start P2, then next what will compression means? You will apply pressure. Okay, P2, initially P2. This is a state, system pressure P2, outside P2. You have to disturb to carry out any process. So what is the disturbance? P2 plus dP. Then there will be a little squeeze, dB squeezing, contraction. Then this way you are moving. So exactly you return to this. So this is how you carry out reverse path, which is compression. compression. One is expansion and the compression. Another attribute is work done by the system in expansion, work done on the system in compression, positive in expansion, negative in compression. These are easily found out, and we already know. So what is this? Is the forward path, forward, and then this is the reverse path. Compression. This is expansion. This is compression. So exactly this point. So you see, you apply here. You see, follow how it is reverse. I don't do this. So you follow. So follow this. Start P2 plus dP. Yeah, on it. But contrast it with the irreversible process. But an irreversible process, an irreversible process it is not that it cannot be reversed. Irreversible process can also be reversed. Means system can be brought back to the original state, but only considering some change in the surrounding elsewhere, allowing some change in the surrounding means also. But an irreversible process can also be reversed. Can be reversed only after producing changes elsewhere. Elsewhere means surrounding. That is you can actually make the statement yourself. That is, when the system is returned to the initial state, surrounding is not. That is the permanent change. Okay, when the system returns to the initial state or original state, to its initial state, surrounding won't. Means permanent change. Surrounding state will be different from the initial. There is a permanent change elsewhere. That is, can you tell me? Third one, there was a perfect backtrack. There is no backtrack. So there is. So how? From graphically, how you know? There is no perfect backtrack. I'll explain you these things, okay? So you are clear. I'm removing this since you are already reversible or what? Irreversible. Okay. Again, let us resketch. Irreversible. Follow this. Follow. Again. Start state 1. State 1. P1, V1T, taken to state 2, P2, V2T. How? Or remember, there is a thermostat here. I didn't sketch that. Thermostated, isothermal process. You understand from here. You understand this isothermal process. Okay. So how you proceed this irreversibly? How many ways you can carry out an irreversible process? How many ways? 3. No. Infinite ways. Finite driving force. What matters is a finite driving force. And finite values. Infinite number of finite values. Between P1 and P2, infinite number of. So, but we will consider which one? The commonest or simplest. Okay. Which is this? P1 initially, what shall I do? Expansion for forward. Sorry, I'll knock it off. Replace this by P2 itself directly to the final one. You are yawning too much. Don't do this. P1 to P2. What is this? Abruptly changed. Abruptly changed, then it will move up through non-equilibrium states. This side is kind. Every day you must be updated with the class. Otherwise you will not be able to follow. Go back home and read through this, study this material, and then you will be able to follow this. This is what? What is this? Okay, forward. And what is this? After all, expansion. Okay, how to sketch this? Here, how to sketch? I have already shown how to sketch this. P1 abruptly drop to P2, then the expansion. Given double arrow to distinguish it from the reversible. So these are all discussed before, but today I am taking up another feature, one new feature, that is this. Okay, then how to return? This is the forward expansion, and return is what? Tell me. I am writing here. So you are here, state 2. Here, system is there. You return, it reaches there through non-equilibrium. Recall, I am not sketching now. I am not showing this because you know this. I don't want to actually make this untidy or say unclear. Because happy. So this is P2. Then what you will do this? What will you do with this? P2 start here. I'll get back to 1. So P2 to P1 commonest. You see compression. So this is the compression. So P2 to P1, what you call this? Backward. P2 to P1 backward or reverse. And what is this? Compression. Compression. So you are all set. How you show here? Let us see. You show here. This is the irreversible forward. Now you see how you draw. Draw this. Say, repeat. You want to drop expansion. P2 to up to P1 and squeezing volume. So this is the diagram. Again, if I may use this double arrow and dotted line for non-equilibrium path, non-equilibrium states. So this is your irreversible forward. You can note this. Irreversible forward. And this is your irreversible backward. Does the forward backtrack in the reversal path? Does it backtrack? This is okay, not lying, is not superimposed here, unlike there. So this is here, this is there. So this is the meaning of this. So irreversible. System is returned to the original state. System has returned to the original. So 1 to 2 follow. 1 to 2, 2 to 1. System returns. But due to this effect, surrounding will not. Surrounding will not. And what is the graphical picture, graphical representation is that, sir, no superimpose. If you say, you may argue, sir, you draw this way. You draw this way. You say, no, why are you drawing this way, sir? You draw this way. Is it possible? First compression. First change. Achha, this is very good. Now another thing I tell you what, in case of irreversible path, note another thing here. In irreversible path, you just note further. In reversible expansion, what is dW? Tell me, the way we have carried out, tell me any place there is P anytime, P external. P external dB. That is P minus dP dV dP displaced, and this is equals to P dB. P minus dP is P dB, but dP integration is not 0. P minus dP is P minus 0. In minus plus dP is ignored. In minus. In reversible compression, tell me what you will. dW is P external dB is P plus dP is again P dB. Acha. In irreversible, you just note, in irreversible expansion, you just finish this part. Reversible, irreversible expansion, compression, work done. Reversible, irreversible expansion, compression, and corresponding work done. See, irreversible expansion, again tell me, dW is what? Again write in the same manner. It will be what? P minus delta P, anything finite. Is what? Tell me, is not PdB? Is not at all PdB? Oh, sorry. Is not PdB? In fact, tell me, less than PdB. Less than PdB. See, P minus dP, delta P is greater than dP. dP tends to 0. Delta P any finite value. So PdB. So you can note here. I will tell you comment. Acha. This is okay. So comment. dW reversible is greater than dW irreversible. And comment expansion. Work done by system. Expansion. That means work done by system. dW reversible, that is at finite you are interested, maybe W reversible greater than W irreversible. You can see from here, and you say comment expansion, and again tell me here compression. Achha, this is okay, very good. Expansion is irreversible, and compression, comment expansion, comment 1, comment 2. Just start this place. Start. I think you don't need this. Write nicely. Take time. Comment 2. Comment 2. What is the comment 2? Compression. For compression. Compression means work done on system. Negative. That's all these things. Okay. You write this. While we write expansion. Achha, write here also write. Okay. Right here, if possible, work done on system, by system. Expansion, work done by system, and you write positive type. Positive. Why positive? Because dB is positive, expansion means dB is positive, so positive. So you write here similarly, compression, work done on system, and negative because dB is compression. If you see here PdB, but dB is negative for compression, so work done is negative, as it should be, work done on system. But in the same way, what you comment here, dW, you look this, take a look here, irreversible. Actually, I have not finished one thing. Irreversible expansion I have written. Irreversible compression I have missed. Irreversible compression I have missed here. So what shall I do? Since it is already written, can remove this. Here complete this. Irreversible compression like this. Reversible compression, expansion compression, irreversible expansion compression. I am sorry. What you write? dW is again P external. dB is what you write here. P. This is P plus dP, this is P plus delta P. dB, and it is again is not PdB. In fact, greater than PdB numerically. plus delta P, but dB itself is a negative thing, but numerically, this is important addition, numerically. So I am writing this here. In contrast, compression work done by system dW, what I am going to tell you here, dW irreversible in compression, dW, yeah, right, irreversible is greater than, I am writing, is greater than dW reversible, greater than. But how? Can you tell me why greater? That numerically, not algebraically, not you can check here, follow me. You can check here. Or dW, have I written there? dW have written, or W I wanted to tell you. Okay? dW is actually, W will be likewise reversible. That is, right, that is W irreversible, also. You write this also. I will show you here. See, number of ways, follow me. Expansion is over. Reversible expansion and irreversible expansion over. Follow. Reversible expansion, irreversible expansion. This is greater, I have shown there this way, or graphically area under the curve. Area under the curve, this is area under 1B2, give a name here, 1B, maybe 1B2, this is 2C1. Area under this curve, so this is smaller than this curve, area under this curve. In contrast, in case of compression, follow this. Compression is this, again area under the curve same, but this time area under the curve is greater. But one thing, why is numerically greater? Area is greater. This area under this curve, this vertical line does not produce any area. So this area is greater. This area is greater than this area under this curve, this path. But not algebraically, because algebraically what is happening, sir? Sir, dB itself is negative, sir. Volume is decreasing. This is decreasing. So that means, like example, e.g., suppose this is minus 8 first, 8 greater than 4 numerically, but these are not 8. This should be minus 8 and minus 4. Then you hesitate to say that minus 8 greater than minus 4. That's why it should be considered numerically, because numerically makes sense. You have to do more work, greater work than this. Why greater work? Now conceptually greater work, why? Follow greater work. Can you tell me how will you returning P2 to P1? Follow P2 to P2 abruptly to P1, the initial pressure, higher pressure. At compression, work done on the system. With which pressure you are working? The greatest. P2 to P1 in this domain, P1 is the greatest and P2 is the least. So P2 to P1 irreversible, and reversible is what? P1 at the end only. P2 plus dP, recall P2 plus dP, P2 plus 2 dP, P2 plus 3 dP, at the end P1. So the highest pressure is applied at the end. So that is P external, okay, P applied. What is that, sir? P external. That is the pressure, external pressure is greatest, in which case irreversible, because throughout the process is P1, the highest pressure, and they are at the end that value, and preceding to that all pressures are less than P1. P2 plus dP, P2 plus 3 dP, finally to P1. So this also your concept, adds to your concept. Yes, sir. Oh, work is, surrounding is doing more work, more pressure. P applied. Remember, it is compression applied, pressure applied. P external applied, and in case of work done by system, expansion opposing system doing work against opposition. Your system is worked upon by surroundings. So you see clearly, so both are negative, but considering sign minus and minus 4, okay? So if you cancel this, then numerically, not again once more, numerically. One student of mine said, sir, this is still holding good, sir. That DW reversible, I will remove this. This I make comment one, DW reversible or W reversible is greater than W irreversible, it still holds, sir. So say, yes, sir, still holds. Why it is greater? No, so it is negative. So negative data means less actually. So he insisted that it still holds, but we should note this, that this is actually amount of work, area under the curve clearly shows greater in the irreversible than in the reversible compression. Reversible. So these two parts are over. Again, so in this context, let me complete that analytically. So analytically, this was actually not completed for want of time. Analytically, what W reversible is greater than W irreversible for isothermal expansion. And most I am not writing all this as expansion. Means again follow expansion, reversible, irreversible. Quickly, what is the W reversible? I will not spend much time on this. Integration PdV. Because dW reversible is what? PdV. It's P minus dP dV. Integration of that PdV. How will you integrate this? From 1 to 2, state 1 to state 2. P is what? nRT by V. Ideal gas. For isothermal expansion. nRT by V dV quickly. 1 to 2, which is what? You know very well. nRT ln V2 by. You can very easily derive. And what is important? This is reversible. Irreversible, I am writing here. You come down. Compare. You answer this. W irreversible is what? P. Start with this. Remember, dW irreversible is what? P external dV. What is the external? That part P2 itself, P2 dV, and then the W irreversible will be what? Integration P2 dV. Remember, P2 dV, what? 1 to 2. Remember, this is not a constant pressure process, but during the expansion it is P2 constant, P2 into V2 minus V1. You have to show that this is greater than this quickly. Quickly I am showing, and remove this part. I am removing. You continue process. What is this? nRT is what? nRT ln V2 minus V. I am writing this way. 1 plus V2 minus V1 by V1. Happy? Is what? nRT ln 1 plus x. If you recall, ln series ln 1 plus x is a series x minus x square by 2 plus x cube by 3 minus x4 by 4, etc. So for small value of x, two are advantage. If it works with small value or large value. For small value of x, for small changes here. V2 minus V1 small changes. For small value of x, what is this? ln 1 plus x is approximately itself is x. Ignoring the higher terms. Higher power, terms with higher power. So ln 1 plus x. So what it will be? Tell me what it is. X is what? V2 minus V1 by V1. Happy? So this is what? nRT by V1. Can anyone tell me? I will be very happy. See, all pictures, all figures are here. All illustrations are here. All states are well defined. Can you tell me what is nRT by V1? nRT by V1, anyone? nRT by V1, take a look, is P1 itself, is P1. Is P1 times, and what is this? It is greater than, tell me, it is wrong or right? Greater than P2, because P1 is greater than P2. Because since P1 is greater, so this analytically you have proved this. Now make some notings. Follow me. This part is clear. So isothermal is over. Note, it is very popular comment that reversible work is greater than irreversible work. Popular notion. That is W reversible, but you should note that this is true when isothermal. Not only that, I will tell you now, in adiabatic also same result. So you note this, that will be good enough. Greater than I am writing means expansion consider, concept is important, that valid for what process you know, so far you know, isothermal, but I add that and adiabatic when I will discuss, and adiabatic. These limitations are not well known. You should note this. But why, sir? In constant pressure? In constant pressure, here, in constant pressure and constant volume, remove all these things. Okay, so over to. In case of constant pressure and constant volume process, B processes, what is this? This is not valid. W reversible is not greater, rather equals to. You note this important point, that they are not necessarily greater. Reversible work not necessarily greater, sometimes equal. This I will show you. You note this point. Okay. Over this part I wanted to tell you reversible. So three ways you will tell that reversible work is greater than irreversible work. I showed you here. Remember, one is graphically area under the curve. Another is analytically I have explained. We have established. Third is what? Conceptually is what? Expansion. Oh, opposition is greater where? Opposition is greater where? In reversible work. System is overcoming greater opposition in case of reversible expansion rather than in comparison to irreversible expansion. This I explained, no? Opposition, and in case of this external, and in case of compression, applied values. Okay, this I discussed about this. So work done by system is greater, and work done in system on system is less. This part discussed. What else I want to discuss? This point is over. Okay, next point is, let us consider now a constant pressure. See, I have noted constant pressure and constant pressure. Let us take up this constant pressure. Then you will see why there this reversible works is equal to irreversible work. Let us remove all these things. Now consider constant pressure and constant volume quickly. So remove this also. Remove all this. So now consider constant pressure. First constant pressure. Pressure P, reversible and irreversible path. Let us now compare. Consider and compare. Let us first carry out the process. Carry out the process quickly. Carry out the process. Quickly, follow me. You try to think how to carry out the process. Constant pressure. Since pressure is constant, you know, state 1, you know, n moles of ideal gas. Same time. What you are doing here? What is the state? Since pressure is constant, it should be P only. This is the state 1. Now what load is here? Okay, load is what here? Tell me. What load? External must be same. Surrounding. P, balancing. Equilibrium. State 1 is equilibrium. Next is what? You want to carry out a process. State 2. You are interested to take it to state 2. What is the state 2 defined? In a constant pressure, tell me, P cannot be changed. Acha, now you see how to carry out. This time can you carry out P minus dP, dP, where you go? There is no change in pressure. P1 to P2, you can do. Isothermal. P1 to pressure changes there. But in pressure does not change. You cannot touch this. Don't touch. Don't touch. Touch elsewhere. Where you touch, follow. This is also a kind of initial state. State initial is what thermostat. What is a thermostat? Means surrounding. Thermostat. Very interesting. How you carry out surrounding. Thermostat means surrounding. What is the temperature? Initial, tell me, guess. T1. Perfect harmony. T1 initial state. Start means initial, and initial temperature same, and pressure external, internal, volume is V. V1. Next, how to carry out T1 to T2? Reversible. So I am writing reversible mode. Then I am so reversible what? T1, remember note here. Can you tell me T2? T2 greater than T1 or less than T1? Tell me T2 greater than T1 or less than T1? Why? Because volume has increased, pressure remaining same, so T2 greater than T1. Yeah. Gas will be hotter. So reversible T1. Okay, how to proceed? Yes. T1 to T2. Can I make it T2? Do you have any objection? T2? No objection, sir. No, you cannot do this. There is finite driving force. No finite, sir. Infinitesimally small. So how shall I change? There is infinite number of thermostat stacked here. What time is it? Infinite number of thermostats stacked here. Infinite number of thermostats stacked here. So you can take any. So T1 is dislodged to what? T1 plus dt. Plus, note plus, temperature is higher. Then it is dislodged further. T1 plus 2 dt. And this continue. T1 plus 3 dt. You may write this. All. So one is here, see, follow this way. Strip off this thermostat, and then replace with that T1 plus dt. T1 plus dt. Then what will happen? The temperature rises. This is T1. Temperature difference is there. So there will be correspond to the temperature. It will be T1 plus dt as well. If it is T1 plus dt surrounding, it is T1 plus dt slight increase in temperature. And for otherwise pressure constant, volume constant, what will happen? Volume will temperature increase, pressure constant, volume will increase. dV for dt, dV this much. dV rise in volume. Then what will be? Further, T1 plus 2 dt. Further. Ultimately what? Last is what? Tell me. Last but what? T2. So infinite number of thermostat you must have provision, and provision for. So this you will use and take the system from state 1 to state 2. This reversible, I will stop here. Irreversible, how you do? Guess, can anyone tell me? This I will sketch next day. Today teacher is waiting. I don't have time. T1, yes? Abruptly. Sir, T1, T2, sir. Finite, sir. T2. This I will sketch next day. So the driving force is what? dt, sir. dt. So T1 it was here. Now it is T1 plus dt. So driving force is dt. And it will be T1 plus dt. System will be T1 plus dt. And corresponding volume change dV. And continues. Thank you so much. I will take up from this point and explain further. Thank you. So tomorrow class.